those all correct? How do you guys feel about those? Each of them have some small challenges. Not unsurmountable though. First one, you don't know immediately what the last term is, but you can plug 15 into it. Remember the thing that sits next to the summation notation is the explicit rule, right? So you plug in 15 to get that last term. But 72 is what belongs here, not 15, right? So we have A1 is 2 and A15 is 72. So that's, I think that's what you should get. 555 is what you got. On the second one, the challenge is, you know right away what A1 and AN are just by looking at it. The challenge is to find what N is. So this is small enough that maybe you can do it by inspection, by just counting them or something. How would you do it what if it was like 140 terms? How would you do that? Like, how would you do it? I mean, how would you know what N was if I just wrote it this way and it ended up being true that this is like not 14 but 140? You just write them all out and hope that you can count them or something. We kind of mentioned this the other day, but go ahead.
Do you like find the range and then divide by common difference and add 1?
Right, which amounts to you solving the following algebraic equation, right? Negative 42 equals 10 plus n minus 1 times negative 4, right? Solve for n, right? Which is what you just said, actually. Take the last term, subtract the first term, divide by the common difference. That's how you'd solve this. And then add 1, actually, right? Did you say that too?
Yeah.
Okay, good. Right, so anyway, one way or another, or maybe by inspection, I don't know how else people found it, but you might actually need to solve this equation to figure out that n is 14. Yes? That was maybe the tricky part on B. On C, you need to remember that there are 21 terms. Is Ryan right? N is 21 here? Why is that true? I see 20. Maybe he just misread it.
It's 1 through 20, that's 20, we can't add 0, so it's 20.
Yeah, this is actually 21 terms, right? Is everyone clear on that? If you don't like this and you want to re-index it, feel free, right? You can have this go from 1, remember how to re-index, from 1 to 21, and have this be k minus 1. That might be the way you're normally used to seeing it. I just want to make sure you're clear on doing that. I think there might have been ones on the homework that might have thrown you off on that too, right? You have to be really careful about that. Okay. Anything else you want to say about this? Did you get these in? Everything's right? Everything looks good? Before we launch into the deep waters, the deep and fast-moving waters that we're going to launch into today, I'd like to make sure you're okay for the quiz. We have a quiz tomorrow. Did you know that? Okay. It's on the schedule. It's on the board. Okay. So the quiz tomorrow covers homework 1 and homework 2, right? The ones you've just been doing. So if you have any unresolved things before we launch into something new, speak now or forever hold your peace. Go ahead, Alana. Yeah, so in this particular case, it's a little weird, right? Where the first term is we're asking to sum this sum. It's unambiguously true that we want you to plug in 0, 1, 2, all the way up to 20 and add them up. Isn't that? I think we all agree on that. So in this case, we want to consider the first term A0, right? Like the first term is what happens when you plug 0 in. Even though I know that's a little uncomfortable because it's like the first term should be indexed with 1, right? But, so that's why I said if you don't like this, feel free to rewrite it. Here, for you, Alana, new problem. Okay. There you go. Okay, forget the problem we had. This is your problem. Go for it. Ready, go. And of course, you'll get the same answer, right? Well, of course, these are the same sum. But I realize, yeah, that sometimes the index makes you uncomfortable, but I want you to make sure you understand those to be the same thing. Helen?
And why is R important?
Because, I don't know, if you were to actually, if you're not convinced, first of all, when I write it this way, I think it should be obvious because the rule for a geometric sequence was A1 times R to the n minus 1, right? Or here with k's and whatever, okay. So just by the algebraic form of the expression, I'm pretty convinced that R is 3/4, right? But also, you could start writing out the terms of the sequence if you still weren't convinced. The first term is 2, agree? If you plug in 0, or down here if you plug in 1, you get 2, yes. The next term is 2 times 3/4. Wouldn't you agree? The next term after that is 2 times 3/4 squared. So then you could look at it and be like, oh yeah, we're multiplying by 3/4 each time. So one way or another, you need to convince yourself that r is 3/4 for sure. Yeah, that's going to be an important skill going forward today for sure. Yeah, Fonda. That would be also still geometric, right? And if you didn't like that, then yeah, you don't like the fact that like it would still be geometric, right? Yeah, okay, so say you're asking, like, what would happen if we had the same exact problem, but we had 3/4 to the k, what do you want, k minus 5 or something?
Not like k minus 5.
Or k plus
like,
10 or whatever you want.
It's like the whole thing plus 5.
Plus 5 over here?
Yeah.
Yeah, that's a good question, actually. That's a great question. I thought you were going to ask something else. Okay. Good. Someone want to resolve that for us? This is a very interesting question, because this is no longer geometric, right? But that's actually tractable for us as pre-calculus students using techniques we've talked about already. What is it? Yeah, you can split it up, right? And actually, what is that piece over here? This piece is geometric. This piece over here, well, it's not really arithmetic in the normal way, but it would be the sum we computed. So Phil is right. It would be the sum we computed, which is 7.98. Plus the sum from 0 to 20 of just 5. You know what that is? This piece is 7.98 because we said so. This piece is 21 times 5, yeah. Because it's 21 5s, right? All right.
We start for the first problem too and like do the sum of like.
Yeah, the only piece, yeah, you could break the 2 up. You could pull the 5 out. The only thing you still have to worry about is there's an n in there, and you'd have to think a little bit about something arithmetic at some point, wouldn't you? But absolutely, you could break it up using all those rules. Yeah. I kind of suggested by the form of the problem, because of how it's written, that this is arithmetic. Like, I wrote it in exactly the form that we like, you know. So I was thinking you would do what Philip did, you know. But you do whatever you like, provided that you get the same answer. Hopefully you did it right. Okay. Yeah, so it's for tomorrow. We need to know everything about arithmetic and geometric sequences. We need to know how to find their explicit and recursive rules and express things that way, and some things that aren't necessarily arithmetic or geometric. Be able to maybe think about those as well a little bit, just as much as you did in homework 1 and 2. We had evaluated infinite limits, right? The limit of infinite sequences as well. Just thinking about the right-hand asymptote, horizontal asymptote. Semester 1 style. And then we also know how to do this kind of stuff, right? Sum up. You should have to memorize the formulas to sum up a finite arithmetic and finite geometric series. And hopefully you understand after our time together why those two things work and where they come from. So, right? We proved those in class. And you should be comfortable writing summation notation, understanding it, all that. Okay. So let's jump in to infinite series today. And we're going to spend, I have a couple warm-ups on there, because we're going to spend a couple days talking about infinite series. The stuff that I'm about to talk about is not on the quiz tomorrow, okay, just to be clear. So if you leave with a little bit of a fuzzy head after seeing some of this, don't fret. As long as you're good on the stuff on homework 1 and 2, you'll be all right. But yeah, we're going to spend a couple days grappling with this tough concept. So hold on to your hat. Are you ready? Everyone buckle your seatbelts. Yeah, we should go back and say what we're going to do. We want to be able to sum up infinite. Certainly, we want to sum up before we leave today. Hopefully, you'll know everything about the convergence or divergence of geometric series and arithmetic ones too. And then this other part here too, we'd like to be able to identify when series that aren't necessarily even geometric, when they converge and diverge. And that will be a bigger task. We'll save for maybe the rest of the week. Huh? That's a good question. Yeah, maybe it's like it's one of those words that's its own plural. I don't know. Yeah, series is. I don't know. No, I don't know. I'm making it up. That's a good question. Can you Google it for us? All right, so, and then of course the goal before we do anything else is to even understand what it would mean to have an infinite series. Are you allowed, ignoring all the other things here, are you allowed, look up at top here, are you allowed to put this infinity symbol at the top of a summation notation sign? What? The answer is amazingly yes. But we have to kind of stop and say why that makes sense and what sense it makes. Yeah?
Series is both singular and plural.
There you go. That's what I was going to say, but you know, you don't know until you ask Google. You don't for sure. So how can we understand this? Well, I want you to think about not putting infinity there first. Why don't you put there? Why don't we just be conservative? Infinity, I don't understand, Mr. Chase. But I am fine with you putting like 10 million up there, right? That's fine with me. Okay, do it. Now, when you're done, also do a billion. All right, and then are you done yet? You compute that sum? All right, now do a trillion. Okay, you done? Now do a quadrillion. Okay, are you done yet? Okay, so now the question is, are those answers you're getting each time I ask you to sum up, not the infinite sum, but let's call it the partial sum? Because it's not the infinite sum. The sum we really want is the infinite sum. Every time I ask you about the sum with this upper limit as 10 million instead, I'm asking you about the partial sum, right? It's not the whole sum. And the question is, are those partial sums, as I ask you, increasingly larger? Sum for increasingly larger. Are they getting closer to a number? Let's call it S. That's the question. If so, then this symbol has meaning, and this sum, we would say converges. The series converges. Okay. So this is the formal way to write what I just said, right? We interpret this to mean, if you ever see this symbol up here, if you don't like it, that's fine. It's fine. It really just means this right here. You see it? And for any given fixed n value, even if it's 10 million, you're fine with that statement, aren't you? It's just going to be the sum from k equals 1 to 10 million. And I would just like you to consider each of those partial sums, right? And let that partial sum become bigger and bigger, and, excuse me, take more and more terms. And ask, is there some trend? Is there some trend? For example, you might already have had this suspicion in the warm-up today, right? Let's return to the third part on the warm-up, right? It seems like something maybe is afoot, right? Did you see that part C on the warm-up? What would happen, I'm just going to try and reproduce the warm-up up here. It was the sum from, this is part C. Yeah, we'll do it from 1 to 21 here. How about 2 to the 3/4, 2 times 3/4 to the k minus 1. All right, so there was the sum on part C of the warm-up today. We got 7.98, I think, right? Right? Okay. Good. So my suspicion, let's just verify this. If you still, maybe you still even have this in your calculator, right? I'm just wondering, what would happen if you changed this from 21 to 100 or something? Do it right now if you haven't already. And maybe if you have a conjecture. Some of you are already like dying to give a conjecture. What do you think is going to happen, David?
It's going to go to 8. 2 times 1 over 1 minus 3.
You think it's going to go to 8? Is this conjecture? All right, let's see. Yeah. We'll see. I mean, we don't know. How do you know that?
2 times 1 over 1.
What are you uttering? You're uttering nonsense to me. I don't understand what you're saying. I haven't learned anything about those crazy formulas you're uttering. Okay. What did you find? Anyone actually doing it? You still have that formula in your calculator. Just do second equal, what is it, to get your last entry up, and then just put in 100 instead of 21, or put 99 or something like that. And what do you think? Are we confirming that it's getting closer to 8?
Yeah.
Right, so if you see something, like I said, something is afoot. Don't you see something happening? It seems that so this is us doing exactly that, right? Plug in 21, plug in 22, plug in 23, plug in 24. Let that number, that top limit of summation up here, tend toward infinity, and tell me what kind of trend you're seeing. What kind of, you see there's two limits happening here, right? Right now we're talking about the limit of the sum, right? And actually, let's come out and say it right now. There are two limits that we're doing. One of them is the following limit, as k goes to infinity of 2 to the 3/4 to the k minus 1. 2 times 3/4 to the k minus 1. And then the limit we're now thinking about is the following limit. The limit as n goes to infinity, it's an n, of the sum of these things. Okay? All right, so like I said, there are two things we're thinking about the limiting behavior of. Let's go back to the basic question. This is the kind of thing I could have asked you on the first day when we were doing the limit of an infinite sequence. And my question about this is like the same I might ask about first semester about this exponential function. Isn't this an exponential function, really? In fact, it's not just any exponential function. What kind of exponential function is it? It's exponential decay, and from Algebra 2 knowledge and whatever else you've learned this, why is it exponential decay? Before you even graph it or anything, you plug numbers in, you know it's exponential decay because, because this number here inside the parentheses is less than 1. Okay, it's exponential decay. I think it converges then to some limit. What is then that limit? What is the horizontal asymptote of this exponential decay function? What does this tend toward as k grows large? 0, yes? Right? Isn't that the horizontal asymptote? If you're not convinced by that still, plug in 1,000,000 and see. You'll get something very close to 0. Right? Okay? That's one limit, and then the one that we just claimed, the claim we just made, said formally, we would say it this way. Equals, what did we claim we think the third part of the warm-up would be going toward if we made this infinity? We think, we haven't proved it yet or anything, but we think that limit is 8, right? You understand the difference? One of them just asks about the terms themselves, right? The terms themselves are going to 0. But the sum of the terms, we claim, the infinite sum, is going to 8. That's at least our claim. We haven't proved that yet, and there's still a little bit of a mystery to us. But this is what this means, this symbol here. It means this. It means the limit as n goes to infinity, or whatever else other favorite lettering has. Okay? I want to make sure we unpack this, because there's a lot being said in this bright yellow box. Let it sink in for a second. So now we have the two notions, right? We have the convergence of a sequence and the convergence of a series, and those are two different things. One might converge. Here both converge to two different things. One might converge and one might diverge. Both might diverge. Two different questions is the point. They're related. All right, so let's start asking the question, when do infinite series converge? Well, we can say, just because we have these two categories of series that we've already been discussing, let's say something about arithmetic series first. Infinite arithmetic series, there you go. No matter what they are, no matter how they look, no matter how slowly you think they're growing, always diverge, right? And we'll actually say more about that later. I just wanted to get that out of the way, okay? The thing we really want to think about today is the sum of an infinite geometric series. Of an infinite geometric series. So here's an infinite geometric series of the kind we were just looking at, in fact. A1 times r to the k minus 1. It converges. We should first say that sometimes it converges, and sometimes it does not converge. And that hinges on whether that r value, like in our example from the warm-up, whether our r value is like 3/4, right? So therefore, it converges. But if r is 4/3, then it diverges. And then the incredible thing is we have a formula, yes, that computes the sum of the infinite series. And we can try it here, right? Let's try it on the one from the warm-up here. Maybe, is this what David was talking about over here? I thought he was just babbling, but maybe he was actually saying this. Okay, all right. What was it? A1? 2? Okay, and then R was 3/4. So that's 2 over, so we're claiming, with this bold claim here, that the infinite sum is 2 over 1 minus 3/4. And does that come out to 8? Maybe that's just a coincidence, though, I don't know. No, it's not coincidence. Why does this work? Where does it come from? The sum of a finite geometric series from Thursday of 2 weeks ago was, what is it? A1 times 1 minus r to the n over 1 minus r. Is that right? Okay? So supposing that r is a number in absolute value, less than 1, right? Then what is happening to this piece of this formula when n grows large, Fonda? Yeah, this goes to 0. When r is less than 1 in absolute value, yeah?
The whole thing goes
No, just r to the n goes to 0, right? And then what do you get? And the answer is this formula, right? Isn't that what you get? If this becomes 0, then you get this formula, right? So, more formally, we can write the limit as n goes to infinity of this is equal to a1 over 1 minus r, provided that r is less than 1 in absolute value, right? Cool. So that's where this formula comes from. It just kind of drops out. It's really just, maybe you could think about it as the special case, the infinite case of the formula you already know. Okay. So we've already kind of thought about this, but let's actually be really explicit about what we mean by a series converging. We talked about, we already mentioned the notion of partial sums, but let's lay it right out there for you. So I've written up here a couple different series, and let's actually compute some partial sums. This is what we mean by partial sums if it hasn't been made clear to you yet, okay? I'd like you to add up the first term of this series. It's like kind of dumb question, but like what's the sum of the first term? Well, of course it's 0.3. I'll do that one for you. Okay. What's the sum of the first two terms of this first one here? 0.33, yeah? Okay, this is not a brain buster here necessarily. What's the sum of the first three terms? We're looking for a trend in this sequence of partial sums. Do you see what I'm doing? Okay. And does the sequence of partial sums seem to be headed towards something? What would you say it is? Like I said, this is not. What is it? Yeah, a third, right? So actually, I might actually write here 1/3, right? That I have this bold, crazy claim that this infinite sum equals, is approximately, not as approaching, not as almost but not quite, it is 1/3, right? I think at first it's unsettling. People are like, on part C of the warm-up, if we do the infinite sum, well, eventually we get close. We get close to 8. It's not. When we approach, we can get as close as we'd like to. It's not actually 8, though. No one would say, yeah, it is. It is in fact 8, right? It's 8. There's no mincing terms, right? You don't write this, right? It's not like, well, 0.3 repeating is not exactly 1/3. Yes, it is. Yes, it is. Right? And you're not unsettled by that fact at all, right? And there's nothing different about that situation. In fact, this is an infinite, what kind of series is this? A. It's actually an infinite geometric series again. So you could actually use the sum formula for this if you wanted, couldn't you? First term is 0.3. Common ratio is, what is the common ratio?
0.1.
Yeah, 0.1 or 1/10, whichever you like. Does that come out to a third?
Yeah.
Better. If math works. I'm not even going to check it. I know it comes out to a third. Better. Okay. All right. All right. How about part B? I think it's pretty obvious what the answer to this question is over here. Does the series converge? Even before writing out the partial sums. But let's write out the partial sums just for practice. I'll do the first one for you. There you go. And then what? 15 is the sum of the first two terms. 30, yay. 50. Is that it? 1, 2, 3, 4, 5. It said only do 5, but there we could keep going if you want. Are those partial sums converging on a number? No. Infinity, yeah, you could say. So we'll say this diverges. The sum is what we're saying. The sum is what is diverging, right? the sequence also diverges. Okay, what about this one? Let's list the partial sums, because this one's a little trickier maybe, right? But the first partial sum is, again, I'll do it for you. There you go. 3. What about the first 2 terms? 0. First 3 terms? First 4 terms? Or I think I can continue. I understand the pattern. Okay. And are these converging on a number? On one number? No. So this diverges too. And here's one way to convince you that this is true, right? Say I group, because maybe this was in fact your first tendency. Say I group 3 minus 3 plus 3 minus 3, and I say it that way in parentheses. Then this sum is 0, isn't it? I don't see the problem, Mr. Shapes. Or say you group it this way, negative 3 plus 3 over here. So you have 3, and then negative 3 plus 3, and then negative 3 plus 3, and negative 3 plus 3. Then what's the sum? You start grouping after this, right? These will cancel out, these will cancel out, and we'll have 3 as the sum. This is nonsense, right? The commutative and associative axioms, some of the field axioms that you were taught back in whenever you learned all the rules of arithmetic. A plus B is B plus A, all that, right? Those were binary operations. Addition has always been for you a thing that is binary. It takes only two arguments. You add 2 numbers, right? So what does it mean to have an infinite sum in general? Well, we have to be very careful. The associative property does not work when you have an infinite sum, unless the infinite sum is convergent, okay? So that's very dicey territory. You can't go like just throwing parentheses around, okay? When you have an infinite sum, yeah.
It also goes to 1.5.
Yeah, it goes to anything you want it to go to, actually. Yeah, you can. David and I were having a conversation about that. You can come join us sometime. It's an exciting idea. Okay. So good stuff. All right, are you ready for this is a fun activity. You can do it if you like, or you can do it at home later. Okay. You are the paper master. Okay. You have a sheet of paper, and you have 2 friends who love paper. They do. They love paper. They're equally lovable in your mind. That you like these people equally, and you want to give them a fair treatment. So you have this paper. You're the paper master, and you want to give them each a third of your paper. You're going to keep a piece of paper too, and this is the only fair way to do it. I think right? They each get a third. Okay. So this is your pile, and these 2 piles over here. Those are their piles. Okay. They aren't, I mean, they're good friends of yours, but they're still not quite happy. They really loved your gift of paper, and they would like more. Please. So you say, okay, I'm going to take my piece of paper, I'm going to divide it into thirds, and I'll give you, again, do the same thing, right? They each now have these piles of paper in their possession, and you have this shrinking pile over here. Sad. And of course, they want more paper. They're not satisfied. Okay. So you split this piece of paper into thirds again. Now their piles are growing. Your pile is shrinking again in the same manner. And we repeat this. They love it. They love paper. They love it. They love it. They love it. Okay. This is my pile now. Every time I'm splitting into thirds, I give them 2 of the thirds. I keep a third. Okay. So now I have a question about what is happening here. My first question, which is, I think, a fairly obvious one, is how much paper, as you, the paper master, how much do you have in the end? Yeah, we're approaching 0 very quickly here. I've already looked that way. Okay. How much do each of your friends have? Yeah, they each have in the end, because I've been dividing equally always, and I don't have any left when we're all done with this. If we go to infinity. Yeah, each person has a half. But wait, there's another way to compute the amount that they have, right? They have a third of the piece of paper, right? Plus, wait, let's go back. Plus, what was this? Of the original piece of paper. It's a third of a third. How much was this of the original piece of paper, this little chunk? Yeah, so you gave them a third of the original piece of paper, and then you gave them a 1/9 of the original piece of paper, and then you gave them a... Where is it? There we go. Yeah, that should be a 27. And then a 1/81st piece of paper, okay? So we're making the crazy claim here that 1/2 is equal to this sum. What kind of series is this on the right side? Yeah, it's geometric. The first term is 1/3, and the common ratio is also 1/3. Can you verify using our formula also that this is true? Does that come out to half? Yeah. Okay, so that was your illustrative paper master example. Okay. Let's do some problems here. Was that good? Do you like the paper master problem? You can try that now later with your friends. Okay. Fun activity. All right, so go ahead. These are not meant to be like tricky necessarily. Just ready to go. Try a few here. Do geometric. I'd like you to tell me whether they converge, and then also if they converge, tell me what they converge to.
I just remember like this 1 minus 1 minus 1
Oh, you average.
No, because the common ratio is -1, so 1/1 minus 1 is 1/2.
Oh, we might also do that.
So 3/2, right?
Except of course that doesn't work. It's hard.
It's absolute value.
Yeah, what's this one? I'll call on some random people. Here's another one for people who are bored by these. Here we go. You don't have to do the last one I just put up there. It is fun. How are you doing on these? Lisa, you want to take first? What you come up with? No, you can just tell me what the answer is. 4? Okay. Yeah, and actually here we'll write the work here too. It's, what is it, 2? Is 2 actually the first term, by the way? Okay, if you plug 1 in, you get, I mean, you might naturally think, well, of course 2 is the first term. It's sitting right here. It's in the A. Well, careful. I mean, you make sure that it actually is 2. Plug in 1, and it is 2, right? Over 1 minus 1/2. And did you get what Lisa got? You get 4? All right, that's good. Everything, I think, checks out there. Good. How are we doing on Andrew? How'd you do on that second one? It diverges, right. Someone in my last class said -2. Is that what you got? Did anyone get -2? But of course, that's nonsense. It diverges. It doesn't make sense that if we sum all terms that are positive that we would get something negative, right? That doesn't make sense, right? But it also is because we told you that R has to be, what's the reason it diverges? Because what? Yeah, because 1.5, our R value, is greater than 1 in absolute value. Yeah.
Is there a way to definitively prove that the formula only works for things where absolute value is greater than 1? Because can't I just claim that's a random number out there for the formula?
Yeah, so the one detail that we've skated over is the fact that when we've taught you to evaluate limits, we haven't actually given you the formal definition of limits in this class. So that's the detail that you're missing. But we can make it rigorous, right? So if we could say more about what it really means to take a limit to infinity, and where all those rules we have come from and why they work. But we've mainly appealed to intuition on those. You're right. How about part C? Let's get someone. Alicia, you want to weigh in on part C? Okay. Oh, you're not done. Okay. Does the formula still work if R is negative? Yes. Works great. And you'll get, wait for it.
I like the
I'm going to come back to you on C in a second, Lisa. You take your time. Take your time. Fonda, do you have D? It's 1.5? Okay. I won't show work, but I'll trust her. It definitely converges because R is 1/3, right? And in fact, actually 1.5, we could have cheated a little bit. Paper master problem, right? Wasn't that 0.5? Plus 1? Ah, got it. Okay. Cheat. Okay. Did you get it, Lisa?
I thought it was really long.
You got a really long number. That's okay. What is it? It's going to be 4 over 1 minus negative 0.3. So 4 over 1.3. What is that? So 3.08 approximately, 368. Okay. Actually, you could give it as as an exact number too, whatever that is. I don't know, as a fraction. What is it? 40 something. Yeah. All right. So homework 3 tonight, by the way, says do the book homework and a piece of paper. We're not going to do that piece of paper. Okay.
And E diverges.
Yeah. Does E diverge? Anyone figure that out?
Yeah.
The hard part there, you didn't expect figuring out whether R was greater than or less than 1 to be hard, but thinking about whether that's greater than or less than 1 is hard, actually. Yes. Homework 3, you can show me on Wednesday. I want you to concentrate on getting ready for the quiz. Your partner needs to shape up, man.